Hello guys, welcome back to Techdose, and in this video we will see the kth smallest element in a sorted matrix, which is from Leetcode number 378, and it is based on a searching algorithm. Let us now look at the problem statement. In this problem, given an n by n matrix where each of the rows and columns are sorted in ascending order, return the kth smallest element in the matrix. Note that they are asking about the kth smallest element in the sorted order and not about the kth distinct element. So you must find a solution which has a memory complexity of better than order of n square. So let's take an example for better understanding. In our case, we are given a row wise and column wise sorted matrix in non-decreasing order, and the matrix size is n by n. Our goal is to find the kth smallest element. Let's consider a one-dimensional matrix. It is not an n by n matrix, but I'm just giving you an example that if you have a single dimensional array, then in this case, if they are asking about the third smallest element, then it will be 2 and not 3, because they are not talking about the distinct element. They are talking about even if you have duplicates, you can count them. Okay. Now, if you have an n by n matrix like we have on the right hand side, you see we have taken 4 by 4 matrix. Every row is sorted in ascending order and every column is also sorted in ascending order, you see. Therefore, in this case, if you have to find the kth smallest element, and let's find out the fourth smallest element, what you can do is you can convert this two-dimensional matrix into one-dimensional array and simply get all the elements sorted, and you can find out the fourth smallest element. And in this case, if you enumerate everything in a non-decreasing order, then the fourth element will be whatever fits at index 3. So that will be 2 in our case. Okay. Now one technique can be to just flatten this entire matrix into a single dimensional array and apply the sorting algorithm, which will be n square log of n square. But a better technique could be to just push all the first elements into a heap and then pop out the element which is the minimum out of this, and then push the next element of that row. This technique was already explained in the sliding window maximum problem. You can follow this. The video link will be in the I button, or you can check out the description as well. This can be solved using heap, and the time complexity will be n square log n, and the space complexity will be n square. But this is not the best approach in this case. This is just one of the approaches. Now, in this case, we can observe that since we already know that all the rows are sorted in non-decreasing order, all the columns are also sorted in non-decreasing order. Therefore, whatever will be our answer will be in the range of the smallest and the largest one. In this case, the smallest one is 1 and the largest number is 11. So our answer cannot lie below 1 or beyond 11, right? Therefore, the kth smallest element must be within the range of 1 to 11. And it must definitely be present in the matrix. Therefore, what we can do is we can search in our answer range. Okay, we know the range of answer. So the minimum possible answer, you can say this is lowest possible answer is 1 and the highest possible answer is 11. So if we want to search in this answer range, then one approach we can take is to take n pointers, and simply we can apply each of the pointer to the first element, just like we did in the heap previously. It is a similar approach, but this is kind of a more simpler one. In this case, you just compare all the n pointers, like you can take p, q, r, s, and you compare all these pointers p, q, r, s and see which one is smaller. Whichever is smaller, you just have a counter. So you can have a count value c equals to 0. Now when you skip this, you move it to the right and the count will increase by 1. Again, compare 2, 2, 5, 7. Whichever is smaller, you just skip there. You could have skipped the second 2 as well. When two values are same, you can skip any one. Now the count of elements you have skipped is 2. Now let's say I was talking about the third smallest element. Now since you have skipped 2 elements, so out of these, whatever we are pointing, one of these will be the third smallest element, because 2 elements have already been skipped. So which one do you think will be the third smallest? The smallest of all these PQRS pointers, right? The smallest one will be the next one which is skipped. And if you find out the smallest, it will be 2. Okay. So the answer in this case will be equals to 2. This approach is also valid, and you see that for finding out each element, like for skipping which element do I need to skip, you have to compare all the PQRS pointers. So it is an n by n matrix, so there are n rows here, right? So for each element skip, you have to make n comparisons, find out the minimum out of n elements. And you know that the highest k value can be the last one, which is n square itself. Therefore, the time complexity in this case will be n square, which is the highest k value multiplied by, for skipping each element you need to do n comparisons. Therefore, order of n cube will be the time complexity. But the space complexity will just be order of 1. Okay, because we are not taking any extra space. So this is a simple approach. Not as good as the heap approach, but the heap approach used extra space. In this case, you are optimizing space by taking more time to solve the same problem. So heap approach can be considered better. Since we already know that all the rows and columns are already sorted, therefore we also know that our answer will be in the range of 1 to 11. On a sorted array or on a sorted matrix, we can always apply binary search. So let's see how we can apply binary search in order to find the kth smallest element. Let's say that our kth smallest element k value is equals to 3. So we want to find the third smallest element. So we already know the range of answer. What is the lowest answer possible? The lowest answer possible is 1, which is given by the top left corner. The highest value which can be possible in the answer is the bottom right corner, which is 11. Okay. And we can say this since it is row wise, column wise sorted. So we have to take a candidate. So let's take the candidate as mid, which will be low plus high minus low by 2. This is the technique. I already told you in the binary partition how to do this and why we do this. So the answer will be 1 plus 11 minus 1 by 2, which comes out to be 6. So let's try this out. Like this becomes the candidate, that what if I take 6? Is this 6 the kth smallest element? That is what I am trying to find. So in order to find if 6 is the kth smallest element, thus in the simple approach what we could do is, in every list we could count how many elements are less than 6, less than equals to 6 you can say. So in the first row there are 4 such elements which are less than equals to 6. In the second row 3 elements. In the third row 2 elements, and in the fourth row there are no elements which are less than equals to 6. So total elements less than equals to 6 are 4 plus 3 plus 2, which is 9. 6 is kind of the 9th smallest element, but we are talking about the third smallest element, right? So if it is the third smallest element and 6 is actually the 9th smallest element, then I should decrease the number. Like I will definitely get a number lower than 6, right? Therefore, in order to decrease it, my low value will remain the same, but my high value will be equals to the mid value. You will understand at the end like why I did not make high equals to mid minus 1. There are multiple variations of binary search and you have to adjust accordingly. Sometimes high will become equals to mid minus 1, sometimes it will not be. In this case, we should not take high equals to mid minus 1. By the end, you will definitely understand. So let's just take it. And let's see what will be the new mid value. That will be 1 plus 6 minus 1 by 2. So this comes out to be 3. Let's see how many elements are less than equals to 3. Now in the previous case we had applied the simple linear search, which was again very time consuming. So what we should do is, instead of applying like how many elements are less than equals to 3 on a given row, we should do that by using binary search. And how many elements are less than equals to 3 can be counted, or the first index which is having a value greater than 3 can be given by upper bound. So if you apply, let's say, upper bound of 2 on the first row, then it will stop at index 3, because index 3 is the first index where the elements are greater than 2. Okay, this is the first occurrence in this row. Therefore, for 6 as well, we should have applied binary search. So if we apply binary search on 6 again, then the upper bound will stop at index 4 here, the upper bound will stop at index 3, here it will stop at index 2, and here it will stop at index 0. So you can add up all the indices: 4, 3, 7, 7 plus 2, 9. So again, the answer is same, but for applying binary search upper bound, it takes order of log of the length of the single row, right? So that is log of n. Now again, we are applying the same for 3. So for 3, the upper bound on the first row will stop at index 3. The upper bound on the second row, which is index 1 row, will stop at 1. For this 2 it will stop at 0, and for 3 it will stop at 0. So how many elements did we see? We saw 3 plus 1, which is 4 elements, right? So this is saying that this is the fourth smallest. Okay, 3 is the fourth smallest probably. Therefore what we should do, we should search for a lower number. Therefore your L will be equals to 1 and your H will be equals to 3. In this case, let's take the mid value, and this will be 1 plus 3 minus 1 by 2, which will be equals to 2. Now let's find out the same for 2. So for 2 in the first row, we will stop at index 3. In the second row, we will stop at index 1. And here we will stop at index 0. And here as well, we will stop at index 0. So for this as well, we got the count equals to 4. So definitely I will keep on searching. Low will be 1 and high will be equals to 2 now. So mid will be equals to low plus high by 2, or you can say low plus high minus low by 2, which will be equals to 1. Now for 1 my search will stop here, and for all the other rows it will stop at index 0. So here the count will be equals to 1, which is less than the third smallest element, right? So we should go on the right hand side. So low will be mid plus 1, and low will be 2, high will be 2, and as soon as low and high are same, we will stop there. And whatever is the high value, we will return it as an answer, high value or low value, whatever. So in this case we can say that 2 is the answer. 2 is the third smallest element. You can see that if I had made high equals to mid minus 1, then in this step where the high value was 3 and we had taken the mid as 2 and the 2's count had come out to be 4, in this update for the next value, the high value could have been made equals to 1, which is mid minus 1, right? So that would not preserve the result. So I think if you just do some dry runs, you will yourself understand about should I update it to mid minus 1 or should I update it to equals to mid. And the same can happen for multiple questions when you update low. Sometimes it can be just low equals to mid, or sometimes it can become mid plus 1. So it can vary depending on the type of question you are solving. So let's discuss about the time complexity. How many times do we need to do this binary search here? Like binary search on the range of answer, right? So what can be the range of answer? It will be the maximum minus minimum. You can take the mod of this. This will be the given range of answer. And since we are doing binary search on the range, so it will be log of this, which we can write as log of R, which is the binary search on the range of numbers. The range will be equals to max minus mid. Okay. Now, having seen this, for each of this binary search on the range of answer, we are applying binary search on all the rows. How many rows are there? N rows. And what is the size of each row? The size of each row is n. Therefore, log of n operation is required to find upper bound on each row, and there are n rows. Therefore, n log n time is spent for each verification of, whenever you find a mid value, you need to count how many elements are less than equals to the given mid value, right? So it will take n log n time on the entire matrix, and we are repeating it log r times. Therefore the time complexity will be n log n log r, which is very, very less as compared to order of n square, and the space complexity is order of 1. So this is one of the best approach for this problem. Let's look at the code. I would like to announce about our live training programs, data structures and algorithms, which is interview dose, and system design, which is design dose. If you are looking for making a switch from service to product based, or even make a product based to product based top tier switch and aiming for your dream company, this is the best curriculum you can ever join. I'll be your mentor throughout the cohort, and I will help you clear all your doubts in the one-on-one sessions. You can know more about this by querying us on the WhatsApp number, or you can also visit our website techdose.co.in. In this code, you are given a matrix and a value k. So you can simply find out how many rows are there, and since it is an n by n matrix, you know how many rows and columns will be there at the end. Find out the lowest possible value, which is the first top left corner, and the highest possible value, which is the bottom right corner. And then we have taken a mid variable. So this is binary search on the range of answer, and you can see how I have updated the high value, right? So if the count is less than k, then I will update the low to mid plus 1, and if it is higher than k, then high will be equals to mid, higher or equal. Okay. And this is the function for upper bound, right? And you can like easily solve this. You can read about upper bound, how it is done. Now what can be a follow-up question here? A follow-up question can be, can you implement the upper bound? Another follow-up question is, why have you updated this high equals to mid? So you can give an example and try to make him understand, like whatever example I have given, the same example you can give, and if you do high equals to mid minus 1, then my input will not give correct answer. Okay, so you can take this input and try it out. I hope you understood this approach. Please also practice the heap approach, which was explained in the sliding window maximum problem. Link will be in the description below. Like and share our video and subscribe to our channel in order to watch more of this programming videos. See you guys in the next video. Thank you.